We continue now with the second of Professor Kedlaya's lectures on perfectoid spaces.
All right, so let me start by saying that if you had trouble getting down the URL for the lecture notes that I gave last time, I added a link from my main homepage. So you can just go to this, or if you just ask Google for me, it knows where, it'll find me in a hurry. And then there's a link from there to these notes. These notes have been updated for today's lecture. So if you prefer to follow along, you can open up the file. And so originally lecture 1 included more material than actually fit in lecture 1. So that extra material is now in lecture 2. We'll see if I actually get through the material that's labeled lecture 2, but we'll see. Okay, so today's lecture will be on the general topic of the relationship between the tilting and untilting operations I talked about last time and Witt vectors. So let me start by reminding you, I hope maybe I need to dry the board off a little bit. Right on it. So let me begin by reminding you where we ended last time. Is there a... So last time we were trying to prove the following. So let K be a perfectoid field. We introduced this notion of the tilt, so the K is a non-Archimedean field with some extra properties, and under those conditions, there's an associated field of characteristic P called K flat, and the theorem is that K and K flat have the same Galois group. More precisely, every finite extension of K is also perfectoid, and therefore has a tilt. And then that makes us a bit possible to give the second part of this statement, which is the functor yes. Oh yeah, that would be great, thank you. That way I can bump this up a little bit. I don't know if this will help. But, so the tilting operation defines equivalence of categories between finite extensions of these two fields. And therefore, it defines an isomorphism, a distinguished isomorphism of Galois groups between K and K flat. So that's what we were in the process of trying to prove. So the approach was the following, and it was modulo a statement that I will talk about today. But let me recall the sketch that I gave at the very end of the last lecture, because it went by kind of fast. So we will show later today that, first of all, there exists a surjective homomorphism called theta from the Witt vectors of OK flat to OK. And for so if I take an extension, say E of K flat, and I extend scalars from K flat to E here, so I tensor the Witt vectors of OE are an algebra over the Witt vectors of OK flat, and I tensor over OK via this map, this thing will occur as OL for some perfectoid field L. So this is what I need to show, but I claim that once one knows this, then what I told you last time is enough to recover a proof of this theorem. Namely, well, one thing you might think I'm missing is I didn't say that this is actually a finite extension of K. But in fact, if you can prove this, then it actually follows that L is a finite extension of K. Why is that? Well, if suppose, for starters, that E over K flat is Galois with group G, then from this description, well, first of all, maybe I should make a comment that when I defined what a perfectoid field here is, I allowed the possibility that K is actually of characteristic P, in which case the K flat construction doesn't do anything. It just gives you back K. So for the purposes of the rest of the discussion, it's harmless to assume that the characteristic of K is actually 0, as otherwise K equals K flat, and there's nothing really to check. So if the characteristic of K is P, then this is a triviality. So it's convenient to assume that the characteristic of K is 0, because then I can write L as, well, the thing that you get by inverting P in this expression, which I can put the inversion of P over here, say. Let me use the good eraser here. So then L itself occurs as this base extension of OK. And then I claim that G, of course, acts on everything. G fixes, if I think of G as fixing these things, it acts on this. And the G invariance, well, I can average, because now P is invertible. So I can average, if I have some invariant element of L, and I write it in this form, then I can kind of average over the group action, and see that it's actually equal to an invariant of this element, of this ring. Tensor some stuff over here. And the invariance here, well, we'll see this from the explicit description of it vectors in a moment. The invariants in here are just what you get when you replace E with OK flat, and then you're just getting K. So if I start with a Galois extension down in characteristic P, the thing that I make upstairs will be a field which has K, which has an action of G, and the G invariants are K. Well, by elementary Galois theory, right, there's a lemma of Artin from Galois theory that says that when you have a finite group that acts on a field, then L over K is a finite Galois extension, and its group is G. In particular, the degree of L over K is finite, and it's equal to the order of G, which is the degree of E over K flat. Perfect. So, I mean, yeah, so once you know that, I mean, right, so you need to know that this turns finite extensions into finite extensions. But once you know that it creates a finite extension here, then it will automatically be separable because K flat is perfect. But of course, we're going the other way. We're trying to first lift finite extensions of K flat up to finite extensions of K, and then show that that functor is essentially surjective. But in the process, that will tell you that every finite extension of K corresponds to a finite extension of K flat. There was another question?
Yes, you said that correspondence is missing, but not really natural.
Well, when I formulated it in terms of, in the original Fontaine-Vanderbrugge theorem, I formulated it in terms of the cyclotomic extension and then some power series field. And the fact that the correspondence was not completely canonical has to do with the fact that relating the tilt, if I take the completion of the QP cyclotomic, the identification of its tilt with the completed perfect closure of a power series field had a little choice in it. So when you write it this way, in this case, the identification is completely canonical.
So you said once we have that K field, then once like the base is fixed, then all the finite things will kind of come up.
Yes. So once you know, so given that the identification of the tilt in terms of K, then everything is completely rigid. So in that sense, the construction is completely canonical. Okay, so, right. So this kind of argument shows that if you take so suppose we know suppose we know this construction gives you a perfectoid field, then in the case of a Galois extension, it definitely gives you a finite extension. And if, if E to K flat is not Galois, then I put a Galois closure up here. And then I compare what happens when I go up here with, I sort of compare these two fields and then I compare these two fields. So in any case, I will get that the lifted thing is a finite extension of the correct degree. And okay, so that gives me a functor from finite extensions of K flat to finite extensions of K, and then so let me just draw a picture that summarizes the argument that I said out loud last time. So if I have K and K flat here, so if I take an uncompleted algebraic closure of K flat, then every finite extension inside there corresponds to some finite extension, some perfectoid finite extension of K. So this is a priori not K bar, because I don't know that it exhausts all finite extensions, but it's this is some field, and this is related to something that Sujatha was asking during Denis' talk, I think. If you complete this thing, then this will be the completion of this thing. Right, so this is a union of finite extensions. This is a union of corresponding finite extensions. When you complete this thing, you get its tilt is the completion of this thing. So this thing is algebraically closed, and therefore its completion is algebraically closed. And therefore this thing, because these two have the same truncations, this thing is algebraically closed, and therefore this thing is algebraically closed. So that says that the union of all perfectoid finite extensions of K is actually algebraically closed. Well, if that means if you have some other finite extension of K, it would actually sit inside there somewhere. So it would sit inside some finite, say, Galois extension of K, which is known to be perfectoid. And then, yet again, you can see that it actually corresponds to some field over here. So this thing, yeah. So this is the union of all untilts of finite extensions in here. And so this is some field which is not complete, but when I complete it, I get something which tilts to here. Right, so I know that this being algebraically closed implies that this thing is algebraically closed, which implies that this thing is algebraically closed, which implies that this thing is algebraically closed. Right, so these two, this is like Krasner's lemma or something. It's something about continuity of roots. This is the statement about truncations that I made last time. And then this, maybe this is the one that's, maybe this one is Krasner's lemma. Yeah, if you have a non-Archimedean field and its completion is algebraically closed, if you start with a non-Archimedean field, you make an algebraic extension whose completion is algebraically closed, then this extension has to actually be, well, if this thing is perfect, I guess I need to assume, then this thing here is algebraically closed. Yeah, you mean for this arrow? Yeah, this arrow came from the fact that, right, I had this argument that a non-Archimedean field is algebraically closed if and only if something is true on the truncation. And so the point is that a perfectoid field and its tilt have the same truncations. you match truncations. So you can transfer the algebraically closed property from one side to the other. Oh, meaning like in this case, it would be you take the valuation ring mod P, and then so we know that when you take a perfectoid field and you take the valuation ring mod, say of characteristic 0, and you take the valuation ring mod P, then you get the valuation ring of here reduced mod something of matching valuation. So that's the sense in which, that's what I mean by the truncations match. Okay, so this is the proof of the theorem modulo, knowing that this construction actually spits out the valuation rings in perfectoid fields. Yes? It's not hard to check. So it comes from, the valuation ring, remember the valuation ring of the tilt is somehow the inverse limit of the valuation ring reduced mod P via Frobenius. And so, completion, of course, like the effect of completion, you don't see at mod P. So, so this thing, the valuation ring of this thing mod P is the same as the valuation of this thing mod P. And the valuation of this ring of this thing mod P is a union of a bunch of valuation rings from finite extensions where the perfectoid property is true. So that's what I'm using. So yeah, so implicitly I'm using the fact that if I start with something perfectoid, if I start with something perfect or perfectoid, then on one hand, if I take a union of perfectoid extensions and take the completion, then I get something perfectoid, and that completion commutes with the tilt operation. So the theorem is saying that this question mark here, by definition, a priori, it only consists of the things that actually correspond to extensions in here. It's just after the fact, you know that is all finite extensions of K. So when you're done, you really are setting, if you draw out the subfield lattice between here and here, then you're identifying that with the subfield lattice between here and here. Of course, it's an infinite picture, so I won't draw it. Okay, so now I need to say something about where this comes from. And so this comes down to understanding why one has a map like this and what the kernel of it looks like and how to go backwards from a field of characteristic P to something that tilts to it. So that process is what I call untilting. And so let me get into that now. I should say that this story will naturally lead us towards something else we want to talk about, which is, excuse me. So this story will naturally lead us in the direction of the Farg-Fontaine curves, which we're going to hear about later in several lectures. So yeah, this theta, let me say that in a moment. This theta sort of contains the information about how to go from K flat to K. Because as I mentioned last time, K flat loses information about K. The extra information is effectively the kernel of this map. Okay, so. Yes, so if you have a non-Archimedean field, it doesn't have to be local. The residue characteristic P, then there's a subgroup that corresponds. There's an inertia subgroup, and then inside that there's a wild inertia subgroup. And then, no, past that, let me not get into it. But at least you know that the wild inertia is pro P. Yes. So those filtrations will match on the two sides. So the unramified extensions will match. And so unramified extensions tilt to unramified extensions, and tame extensions tilt to tame extensions.
For example, not only the Galois groups are the same, but if you have patients with that, are the doctors the same?
Well, I don't claim that. Yeah, the art and conductors, I guess, make sense. Yeah. I'm not claiming to be able to tell you how higher ramification works in a non-discrete valuation ring. Okay, so let me go ahead and move on. So we've heard a bunch about Witt vectors in a kind of a highbrow abstract way. So I'm going to use only p-typical Witt vectors, and I'm going to use them in the sort of traditional lowbrow way. So for R, a perfect ring of characteristic P, and perfect means that x goes to x to the p is a bijection. Of course, that means R is reduced as well. The injectivity of this map means R is reduced. So if R is perfect of characteristic P, the ring of p-typical Witt vectors is the unique, up to unique isomorphism, p-adically separated and complete ring whose residue ring, mod p, is identified with R. So, right, it was proved by, I think at this level of generality, I think it's due to Witt at this level of generality. I don't know if he did rings, but I think he did. Right, so what do we know about this construction? So, so this ring admits a unique multiplicative section of the reduction map. Multiplicative. It's written. Put the target in brackets. So this is called the Teichmuller map. Right, so it's not the case that you can write, so sometimes one fancifully writes WR as being morally the power series ring in R with the variable P. Of course, that's not actually how it works, but it is the case that there's a set of elements of W of R which act like coefficients. It's just that they don't form a subring, they only form a multiplicative submonoid. So there's a unique multiplicative section of the reduction map. This is using the fact that R is perfect. And because I have, so to speak, coefficients, every element has a unique representation as, this would be, so to speak, a power series in P whose coefficients are in R. And I like to write bars on things to remind me that they're in characteristic P. So I'm going to write the coefficients as, the coefficient of P to the n as x bar n, typically when I'm expanding x. Okay. For the moment, that's all you really need to know. Later, I'll need to know something about how these coefficients behave with respect to ring operations. Right? The issue is that the bracket map behaves in a weird way with respect to addition, but never mind that for the moment. And I guess I should point out, because this is unique up to unique isomorphism, and R has a Frobenius map, then WR also has a Frobenius map. So there's a Frobenius map from WR to WR, which satisfies Frobenius applied to some Teichmuller element is just the pth power of that. And the p can go, the exponent can go inside or outside because it's a multiplicative map. So I'm not going to say too much about the p derivation point of view. Of course, right, this thing is p torsion free and I have a Frobenius lift on it. So there's an associated p derivation given by the usual formula. So that exists. I'll make one comment about it, but mostly I will be talking about these rings in terms of these coordinates, which up to taking pth powers are the usual Witt vector components. Okay, so as I already telegraphed over here, I'm mostly going to be interested in this construction not when PR is a field, that's the most classical case, but sort of the next level of complexity up from putting in a field is putting in a valuation ring. So so for F, so throughout this lecture, F is going to be a perfect F is going to be a perfect and actually complete valuation ring of rank one, maybe I should say rank one valuation ring. So, I mean, something like, actually, no, sorry, OF is going to be the valuation ring. So F is just going to be a perfect, or perfectoid if you prefer, non-Archimedean field of characteristic P. So I'm going to introduce a slightly different notation for the Witt vectors of OF. It's customary to call this A-inf of F. So this is just another way of writing W of OF, but this notation is sort of commonly used in p-adic Hodge theory, so we will see it in some of the other lectures. So I want to get used to using this kind of notation already here. I won't try to unpack for the moment why it's called A-inf, then maybe that will come up in another lecture. So this is just another way to write Witt vectors of OF. Okay, what do the Witt vectors of the valuation ring OF look like? Well, right, if I take Witt vectors of a perfect field, I get a complete DVR. So that's not going to happen in this case, but right, when you take a local ring and you stick it into the Witt vector construction, you're going to get another local ring because P is in the Jacobson radical. So this is going to be and this is in fact a complete local ring with residue field equal to the residue field of F. Right, kappa F for the residue field of F. This is morally of dimension 2, I'm going to say. Now this is not a meaningful mathematical statement, so I'm putting it in quotes. This is not Noetherian. I mean, it's sort of easy to see that it's not Noetherian because, remember, this is a non-discrete valuation ring. So if I take some element, say var pi in the maximal ideal of OF, then the ideal generated by this Teichmuller and then the Teichmuller of the pth root and so on, I keep taking pth roots, this is not finitely generated. So it's easy to make infinitely generated ideals. It takes a little bit more work to understand what's going on here at a deeper level. So for example, you can show, and I give the reference in the notes, that this thing actually has infinite global dimension. So you can make infinite length, you can make arbitrarily long chains of prime ideals. I'm sorry? Yeah, this is not a finitely generated ideal of A-inf of F. Or were you pointing somewhere else? Yeah, this ring is supposed to has some similarities with a two-dimensional local ring, but it's not Noetherian. But so A-inf of F is morally of dimension 2, but not a Noetherian ring. What does that mean? Let me not go too far into it. One statement that is, I'll just say this out loud because I'm not going to use it, but one way in which this is like a two-dimensional regular complete local ring is that if you take a vector bundle and the punctured spectrum of this, it extends uniquely to a vector bundle over the whole spec. Right, that's a special property of two-dimensional regular local rings. That's not true, say, higher dimension greater than 2. But so this behaves a little bit like a two-dimensional. So this behaves a little bit like. So there's a little bit like. Well, if you want to take an actual two-dimensional local ring, you could take something like ZP square brackets T or something. So it's or you could, if you prefer, you could take FP with two variables adjoined. So there's some running analogy between this ring, which is not Noetherian, and these kind of Noetherian variations of it. And a lot of what I'm about to say is driven by this analogy, but you have to handle it a little bit carefully. Okay, so now we have yet another statement which basically is straight out of Fontaine, which is that for K a perfectoid field, there's a unique homomorphism theta from A inf of K flat to OK such that when you compose with the Teichmuller map, so then now you're going from K flat, OK flat to OK, this is the sharp map from OK flat. OK, remember OK flat is set theoretically the inverse limit of OK via the p power map, so this is the projection onto the last coordinate in that description. So it's not so hard to see that this thing is unique if it exists, because this is sort of telling you where all the Teichmullers have to go, and everything is, it can be written in terms of Teichmullers, so this forces everything. And so the only issue is this actually a ring homomorphism? Is this actually compatible with the ring operations? There's probably some pure thought way to see this. I don't happen to know one off the top of my head, but I mean, there is a functoriality property for Witt vectors of a perfect ring and things with there's some kind of functoriality property you can formulate, but even that I couldn't find a pure thought way of doing that. Maybe I need to stare at this with Jim a bit later, but is equal to the sharp. Remember, sharp last time was defined as this map from OK flat to OK. It's the projection. Yeah. No. It's let me try to make it more like a sharp, not well. You can't really tell. They're octothorpes. You can't really tell the difference. But yeah. So this is the sharp map from OK flat to OK. Right. So maybe I just write this out. So theta of bracket x bar is equal to sharp of x bar. That pins down this map. So once you've actually constructed the map, the easy part is to show that this is surjective. Again, because OK mod, because I know that some truncation of this, like if K is characteristic 0, then, if K is of characteristic P, then this is just reduction mod P, and this is kind of trivial. Otherwise, OK mod P is the same thing as OK flat mod something, and so I know I'm covering OK mod P, and then it's easy to see from that it's actually surjective. So this is the Fontaine theta map, and as we discussed earlier, this map somehow is the extra information beyond just identifying K flat that lets you recover K. So what does the ideal I, the kernel of the theta map, what does it look like? So I claim that I is a principal ideal generated by what Fontaine calls a primitive element, which I need to tell you what it is. But let me just point out that if you imagine that AINF is something like a two-dimensional local ring, I have a quotient from that onto something which is one-dimensional, a one-dimensional valuation ring. Well, the rank 1 valuation ring. And so it sort of makes sense, even if it's not completely convincing, that this kernel should be a principal ideal. There's some kind of vague consistency there, but let me actually make this more precise by telling you what kind of generator this thing has. So these primitive elements, once I tell you what they are, will give you all the ways to realize a given characteristic P thing as a tilt. So actually, let me go ahead and put the definition here. So an element Z of AINF of, so F, remember, F is some arbitrary perfect field of characteristic P, some perfectoid field of characteristic P. So an element Z in AINF of F, I'm going to write it in the usual way as Teichmuller elements times powers of P. This is primitive if, on one hand, the reduction mod P, so Z naught bar, is in the maximal ideal of F. So it's integral and not a unit. And Z1 bar is actually a unit. Now here's the part where I want to make a comment that relates this to delta rings. Equivalently, the reduction is not a unit, and delta of Z is a unit. Why is this equivalent? Because this thing, well, if you work out what this is, this is congruent to Teichmuller of Z1 bar to the P mod P. So this is a unit if and only if this is a unit. So this characterization is the one that you see in the world of prisms. So for example, if you look at this work of Putt and Scholze on prismatic cohomology, this is the point of view that you take to get the analog of a primitive element in their setup. But today, I'm mostly going to be playing directly with Teichmuller components. So well, what's nice about this point of view is that it makes it quite clear that a primitive times a unit is a random primitive. It's not hard to see that from here either, but here you can use the identity for the product, right? So delta of yz is, what is it? Y to the p times delta z plus z to the p times delta y plus p times delta y delta z, is it? I got that right? And of course, so to tell whether this is a unit, this doesn't matter. This is irrelevant. So I just need to look at the reductions of these things mod P, and well, one of these terms, this term is a unit, reduces to a unit in F, in OF, and this thing reduces to a non-unit in OF. So the sum is a unit. So that's kind of handy. Yeah, so that means that primitive elements, any associate of a primitive element is a primitive element. So it makes sense to say that an ideal is primitive. So an ideal I of AINF of F is primitive if its principal and some, therefore any, generator is a primitive element. And this statement is the implication that some implies any. Okay, so now I can show you, so this is easy enough that I can actually give you the proof of it. So lemma is that the generator, so actually, no, let me not do that yet. I can show you, well, so the kernel of the theta map so if K is perfectoid, then the kernel of the theta map contains, so it's easy enough to see that the kernel contains a primitive element. I'm not yet claiming that it's generated. It will be in a moment, but let me first show you why it contains a primitive element. This is pretty easy, right? Because we know, so I choose, again, I'm going to assume the characteristic of K is 0, because otherwise this is easy. If K is of characteristic P, then the theta map is reduction mod P, and so P is itself a primitive element, because then you have 0, this thing is 0 and this thing is 1. Okay, and so the kernel is in fact generated by a primitive element. So let's assume I'm not in the degenerate case. So if characteristic K is 0, then I can choose some x bar in OK flat such that sharp of it divided by P is a unit in OK. Right? This is the compatibility of value groups between K and its tilt. Let's call this thing Y. Now remember, this thing is the theta of x Teichmuller by definition of the theta map, the numerator. These two things are the same. Right, so if I call this thing Y, then because theta is surjective, I can write Y itself as theta of some W. Because this line, the previous line, let me rewrite it actually, such that, so there, I choose an x bar in OK flat such that Y, which is by definition sharp of x bar over P, is an element of OK of valuation 0. See here. And I know I know I can do this because K and K flat have matching value groups. So and this Y, when you divide this thing by P, you can of course write it as some image, the image of something under theta, and then I claim that the element P times W minus x bar is primitive and in the kernel. Well, it's in the kernel because applying theta to this thing is the same as applying sharp to the thing inside. And so, right, this gives you P times, when you apply theta to Z, you get P times Y minus P times Y. So it's in the kernel, and it's primitive because this is not a unit, but this thing actually, W is a unit, because Y, right, theta, if theta maps something to a unit, then the thing it came from must be a unit. So, yeah, so there are lots of ways to write elements down like this, and it's not obvious that any one of them is a multiple of any other, or that in principle there could be some other way to produce elements of the kernel which are not primitive. So I still have to do some work to show that the thing is actually generated by one of these primitive elements. Before I say that, let me say something else. Okay, so why are these things called primitive elements? Well, they're like Weierstrass primitive power series in the analogy with something like ZP double brackets T. And so they admit something like a Weierstrass division. Was that a question? Okay. So there's something like a Weierstrass division for these things, which takes the following form. For I, a primitive ideal, and of F, every class in the quotient ring is represented, not at all uniquely, but there are representatives of this form, by a Teichmuller element times a unit of an of I, an of F. So up to scaling by units, every class can be represented by a Teichmuller element. And I don't want to go through the proof of this. I give a sort of quick sketch of it in notes. The basic idea is that because this thing is a so you start with some, so say Z is primitive generator. And if you have some random element X, what you'd like to do is you'd like to replace X by some translate by a multiple of Z in such a way that you get it into this form. Well, you don't do that all at once. But what you can do to try to make X look better is you can replace it by something like this. So you take X. So you take X and you remove its first sort of leading coefficient. And then you do the same thing with Z. And you use that and you shift by this. So this is, of course, a unit because Z is primitive. And so the idea is that if you do some translation, if you do something like this, then this kind of makes this in some sense makes all of the components of X bar a little bit smaller, except possibly the leading coefficient, because you're kind of ignoring what happens with the leading coefficient. Right, so right, I should maybe point out what an element like this can be characterized. These products have the following property. They're things of the form some yn bar brackets p to the n, where y naught dominates all the other ones. So y is a general product of this form. So any product of this form has the property that the leading coefficient dominates, because that's true here, because the leading coefficient has norm 1. And when you multiply it by a Teichmuller, you scale all the coefficients by the same amount, so that doesn't disturb this inequality. And in fact, conversely, if you have something like this, then you can write it as Teichmuller of y naught bar times the thing that the cofactor is a unit in A and F. So these products are precisely these things. And so in some of my papers, I call these stable elements of A and F. So these are not, of course, Teichmuller elements, but they're the things that are associated to Teichmuller elements. So basically, I'm saying that if you have a primitive ideal, every class in the quotient is represented by an associate of a Teichmuller. And using that, you can prove lots of neat properties of the quotient ring. I'm sorry? Which is not discretely valid. F? Right, F has a value, F is a non-Archimedean field. Not discrete, but it's a perfect non-Archimedean field. So it has an absolute value on it. Yeah, real value. It's a rank 1 valuation. So yeah, so these are real numbers. Yeah, so my valuation rings here are always going to be rank 1. I mean, you might want to put in higher rank valuations if you want to think about adic spaces, but let's not talk about those right now. Right, so using this you can, right, so this lets you prove, for example, that the kernel of theta is actually well, it's primitive. It's generated by a primitive element. Yeah, because if I start with this, I mean, if I start with this z, then if I divide by this ideal generator, if I divide by the ideal generator by some primitive element, then I can't get something, right? So the point is that if z in the kernel is primitive, then what this tells you is that the resulting map, so the map AN mod F, K flat, modulo kernel of Z, this thing to OK is actually, it has no kernel. We'll see another proof of this. I guess at this point we'll do it next time, or maybe the time after. So there's a whole theory of norms and Newton polygons on this ring, which I'm not going to get to today. That will give you another way to see what's going on here. But because if you have something which is not a multiple of z, you can represent it by something like this. And something like this can't map to 0. Yeah, it's the same argument. So if I have something which is not a multiple of z in the kernel, well, I can represent it modulo z. So modulo z, it can be represented like this. And such an element cannot map to 0 under theta. Because this part can't map to 0, and this part can't map to 0. And the target is a domain.
So you apply this propagation modulo z.
Modulo z, right, not modulo I. Because we don't yet know that I is generated by z, but so you apply it mod z. Okay, so now I need to state the tilting correspondence, which is the thing that's going to give me what I wanted from the beginning, is that for any primitive ideal I, so let me state this and then show how this applies to untilting finite extensions, and then I'll stop. So for any primitive ideal I of ANF of F, this thing can be identified canonically with OK for some perfectoid field K with K flat equals being identified with F. That is, you could choose this identification in such a way that K flat is identified with F in such a way that this quotient corresponds to the theta for that K. And so the key point is, yes? Well, I'm defining, you can think of it this way. I take this ring, so if I is not generated by P, then this thing, P will be a non-zero divisor in here. So if you take this ring and you invert P, you call that K, then K is a perfectoid field. And its flat is canonically isomorphic to F. And so the point is that you can use, the key point is to define the absolute value on the quotient. And the idea is that these representatives give you a way to do that. So if you have a representative like this, well, you know this thing had better map to something of absolute value 1, and you know what, and you use the valuation on f to decide what the norm of this should be. And then you have to check that if you have two different representatives, then you get the same absolute value, regardless of which one you use. So that basically gives you a way to define an absolute value, and then you check that using that you actually are getting the valuation ring in a perfectoid field. So this basically is a construction that says these primitive elements generate things with a given tilt. Now and so finally, let me just say how that applies to the case of a finite extension of a perfectoid field. If K is perfectoid, and E is a finite extension of K flat, well, it doesn't have, in fact, even if it's not, I mean, if E is any extension, let me say it this way, if E is any perfectoid extension of E flat, it could be a finite extension, but it could also be just some huge perfectoid extension, then the kernel of the theta map on K it of course generates a primitive ideal of A inf of E, because these properties of being primitive do not change when you go from F to some larger field. So what am I doing to get the finite extensions? Well, I'm just taking the primitive element that I used to recover K from K flat, and I'm applying that to this finite extension of K flat. That's what that tensor product construction I was doing was implicitly saying, is that I'm extending the primitive ideal in A inf of K flat to A inf of E, and that's the thing that gives me an untilt, which then turns out to be the finite extension of K that I'm looking for. So the point is, if you understand how to untilt a given perfect field, then you can see that a finite extension of a perfectoid is perfectoid. And later in this series, we'll talk about what does it mean to kind of classify the different ways you can start with F and pick this primitive element. So there's in some sense a moduli space of these choices, and that moduli space is one manifestation of the Farb-Fontaine curve associated to F. But I don't have any time to talk about that. Right now, we'll push that down the line. So I'll stop there.
So in this language, how do we revisit Fontaine's rings? Which of the fields that come up are perfectoid?
So Fontaine's constructions, in some sense, can all be made out of, so you would take K to be C, a completed algebraic closure of QP. And then the flat of that is something. I think he calls that E classically. And you would take the A inf of that, and then all the Fontaine rings can be built from A inf of E by various manipulations. So everything kind of goes through this guy. And this map theta shows up in Fontaine's work. You use it to define things like the ring B to Rom, and it's basically telling you that you're supposed to remember that C flat has a particular untilt. Now you could imagine, working with some other untilt of C flat. So it turns out that there are untilts. Not all the untilts of C flat actually look like C. There are kind of weird ones, but you could do a similar thing with any untilt of C flat. And in some sense, the theory of Stuka's in the local Langlands correspondence comes from the fact that you can actually kind of compare different ways of untilting C flat. And those correspond to the legs that show up in Stuka's in the positive characteristic Langlands program. Hold on, get the mic. It's for the recording.
Oh, me? Okay. Just to make one point clear, you allow the Z0 in your primitive element to be 0, in which case
Yes.
the untilt would be F itself in characteristic P.
Yeah, so
all the other cases will be characteristic 0.
Yeah, so when you talk about the Frog-Fontaine curve, you usually throw out the trivial untilt, and you just look at the characteristic 0 untilts. But I tried to say everything so that it was valid in character for the trivial untilt unless I explicitly excluded it. When you start untilting, later on we'll talk about untilting more general rings, and then you can have untilts which are kind of mixed between characteristic 0 and characteristic P, although we won't have too much to say about those, but they do exist.
Yes, I have missed out. It seems that okay. Somehow you did not spell out what exactly theta is.
I didn't say what exactly the I is. I mean, I told you it's generated by one of these primitive things.
No, I mean the map theta, like the Fontaine's map.
Oh, so I told you, I gave you enough information to determine it uniquely. Remember, I told you that when you evaluate it on a Teichmüller element, you get the sharp map. And so that rigidifies the construction, because somehow I'm telling you what everything does mod P, and that forces the whole issue. The only issue left is to check that actually the Witt vector arithmetic on those Teichmüllers is compatible with the map that I'm trying to define. And so there's some computation that you can either do it by some annoying explicit formulas, or you can be more clever than me and do it in some high-level way. But I did tell you enough to give you no flexibility in what this map is. The hard part is to make sure you actually get a homomorphism. But yeah, this computation goes back to Fontaine originally.
Sorry.
Okay. Oh yeah, sorry.
Okay. No, since I mean the whole point was to identify Galois groups, right? So you have to keep track of automorphisms.
Yes.
So one thing I don't understand in this proposition, or at least the way you can use this proposition, is the ideal. I mean, on the right-hand side, OK can have isomorphisms, automorphisms.
Yes.
Which is precisely the thing you're interested in.
Yes.
Whereas I is always I.
I is always
I mean, the ideal is the ideal. So you say if you take I inf mod I, it can be isomorphic to OK in several different ways.
Yes, but right, I also have an identification of K flat with F. And it's not just any identification, it's maybe I should write this down here. Let me make some space here. Right, these two identifications are supposed to be compatible in the sense that if I take theta, and theta is a canonical map from A inf of K flat to OK, and so if I'm identifying K flat with F, then I'm reducing mod I. This is an isomorphism, and this diagram, and the compatibility between the two is that this diagram has to commute. So that rigidifies, that locks F and K together in the sense that every time you have an automorphism of K, it induces an automorphism F from this point of view. And so the compatibility between these two that's in this diagram is what rigidifies things.
I guess you are also saying that all the primitive ideals of I and F are
Yes, I'm saying every primitive ideal of A and F comes from some perfectoid field. That's exactly what this is saying. And so there's a bijection, and suitably encoded, between these primitive ideals and isomorphism classes of untilts of F.
So you said that A inf of F is not really a two-dimensional local ring, but it kind of morally is. So are there, and you gave an explicit way in which it's actually not. They're arbitrarily long chains of prime ideals. But are there any examples which are kind of less, I don't know, chain theoretic, that it's in which respects in which it fails to act like a a regular two-dimensional local ring? Because you mentioned one way in which.
Oh, here's an example. It's not a coherent ring.
Oh, what does that mean?
That means that every finitely, coherent would mean that every finitely generated ideal is finitely presented, I think.
That's a good
So,
one.
yeah, it doesn't have that property either.
Okay.
That actually comes from an analogy with the fact if you take a non-discrete valuation ring, then the power series over it are also not a coherent ring. So this is a very classical bit of algebra. This you know, my former colleague Lance Small wrote down the proof of this in the 80s or something. So it's basically just transposing something that was already known in classical, you know, commutative algebra. But yeah, that's a strong sense in which this thing doesn't look like a two-dimensional local ring.